Let's get started on colligative properties. These are properties that are concerned with the number of solute particles in your solution. Okay, so these are properties based on the amount of solute particles in solution, not the type. Okay, so basically, if I had 0.50 molar sodium chloride solution and 1.0 molar, let's say, sucrose solution, let's make it glucose, okay, they will have the same colligative properties. Even though this is ionic and this is molecular. There is one aspect of your solute that you need to be aware of, regardless of whether it's ionic or molecular. For your solute, it needs to be non-volatile. So in other words, it should have 0 or very close to 0 vapor pressure. Okay, so let's talk about our first colligative property, which is vapor pressure lowering of the solvent. Okay, so vapor pressure line. Why? Here's my beaker. Okay. And here's the second beaker. So let's compare the two. Let's just say that these are my non-volatile solvents, or solute, excuse me. Okay. And these are my solvent. Okay, so let's go through. You're going to end up having it in an equilibrium situation, so you want a closed system. Okay, so let's talk about vapor pressure first in my pure solvent before I start worrying about having a solution with a non-volatile solute. Okay, so why does it lower the pressure? So when I take a look at, let's say, my solvent, okay, what allows it to form vapor pressure? So remember when we were talking about it reaching equilibrium and then you have these in the gas state, you have to have enough energy to break my surface tension, right? So here's my surface tension. I have enough energy to break it and to go into the gas state. But there's another aspect to it too. For this to do this, be aware that if I have a smaller surface area, I have less opportunity to break out and go into the gas state. Okay? So for example, if you had spilled, or let me just give you two containers. This has suppose this has 100 milliliters of water. Okay? And this has 100 milliliters of water. And I have them both in the same room, let's say at 25 degrees Celsius. Which container will be dry first? We're not boiling it or anything, but which one would end up being dry first? This one will, because it has a greater surface area. So I have more molecules at the surface. Remember, because surface tension, I don't have also cohesive forces up here. I only have cohesive forces down here in my solvent. This has fewer attractions than down here. So it's easier to break the surface tension. If I have a huge surface area, then I have more opportunities for my solvent to go into the gas state. Whereas here, I'm only limited to what's right here. And if you spill a glass of water and you wipe it with a towel that's not that absorbent, even if you wipe it with a towel that's not that absorbent, it will evaporate and dry faster than you would if you just let the huge puddle of water stay the same. Okay? So we're talking about the fact that if I'm looking at this, I have my vapor pressure. In the system where it allows me to go into the gas state. Now, does it matter the vapor pressure here or there? No, the actual pressure by the solvent is exactly the same. But if you're talking about the rate at which this will go into the gas phase, I have more of this in the gas phase here because I have basically a large surface area. But what happens when I have a non-volatile solute? Well, now there's a couple things that can happen. First of all, if the attraction with my non-volatile solute in the solution is very strong, okay, then there's a stronger attraction holding my solvent in solution. Therefore, it has less of a tendency to escape. It has to have a greater energy in order to break those bonds, okay, those intermolecular attractions, to go into the gas state. So that's one reason, okay, that you would have a lower vapor pressure. At the same temperature, same amount, I'm not going to have as many solvent molecules in the gas state. There's a second one. So one, it could be your intermolecular. Let me just write it in beer here. To prevent it, if I have stronger intermolecular attractions. And the second is this. Look at my surface area. Here I have all these solvent molecules. Here I have solutes at the surface as well. So I have a smaller surface area, so I have a less likelihood of my solvent molecules even being able to make it to the surface to get out into the gas state. So because I have two forces that are keeping my solvent in solution, I lower, well, actually there's none right here. I lower my vapor pressure of solution is lower. Okay, so the question is, how do we determine what the vapor pressure is of my solution? Okay, and for that, we use Raoult's law. And this is for an ideal solution that we're talking about. Okay, turns out the vapor pressure of my solution is going to be equal to the mole fraction of my solvent times the vapor pressure of my pure solvent. Okay, so two things we're going to do. One, let's derive this equation, and then two, let's go through and do a problem. Okay, so how do we derive it? Okay, so vapor pressure lowering. Okay, if you look at the change in my vapor pressure, it's going to be equal to the mole fraction of my solute, okay, times the pressure of my solvent. Okay, so why is that? Because if I have solute in there, then that's not going to go into vapor state. So the change is how much. If I have a lot of solute, then a large change in vapor pressure. Very small amount of solute and a small change. So the pressure of my solution is equal to the pressure of my solvent minus the change in pressure. So basically the pressure of my solvent minus the mole fraction of my solute times the pressure of my solvent. So I'll just go ahead and do a distribution. 1 minus the mole fraction of my solute times the vapor pressure of my solvent. Well, remember, if I only have a solute and solvent, this is equal to the mole fraction of my solvent. And that's how we get our final equation. P solution is equal to the mole fraction of my solvent times the vapor pressure of my solvent. Okay, so let's go ahead and take a look at a sodium chloride solution. Okay, so let me just look up the vapor pressure for you, and we'll get started. Okay, so vapor pressure. Okay, what I want is, what is the vapor pressure of 0.50 molar sodium chloride solution? Okay, and density of the solution is equal to 1.02 grams per milliliter. Okay, so now that we have that, let's go ahead and take a look. The vapor pressure of my solution is equal to the mole fraction of my solvent times the vapor pressure of my solvent. And you're going to need some information here. So let's say this is going to be at 25 degrees Celsius, and the vapor pressure of water is equal to 25 degrees Celsius, 23.76. Okay? All right. So you can look that up in the table in Appendix B. All right, so what we really need is, this is given. So what we need is this. What is my mole fraction of solvent? Remember, my mole fraction of solvent is going to be equal to the moles of solvent divided by the total moles. Okay, so we need to get the moles, total moles and moles of solvent. So how do we do that? We assume 1 liter of solution, we have 0.50 moles of sodium chloride. That's solute, not solvent. Okay, so we need to find out how many moles of water I have. We also know that the mass of 1 liter of solution is going to be equal to 1,020 grams. This is of solution. To get the mass of my sodium chloride, we can use the 0.50 moles times our 58.44 grams per mole. And that gives us like 29.22 grams of sodium chloride. Okay, so let's continue here. Okay, so the mass of water will be equal to 1020 grams minus the 29.22 grams, because that's my solute. And that gave us a number, it was 990.78 grams of water. And convert it to moles of water. It's basically 55 moles. Okay, so the pressure of my solution, which is 0.50 molar sodium chloride solution, is equal to, we have 55 moles of water, that's my solvent, divided by 55.5, because I'm adding my solute to it, that's my total moles. And so that's my mole fraction times 23.76 torr. So the pressure of my solution, the vapor pressure of my solution is going to be equal to 55 divided by 55.5. So that's 0.99 times 23.76. 23.5 torr. Okay, so it lowered it a little. Now, does that seem significant? But here's the thing. When we talk about solutions, why is this important? Remember, the boiling point, the normal boiling point, is when the temperature where the partial pressure of my solution or solvent, but in this case my solution, is equal to the external pressure. So basically we could say this: if we had my normal solvent, water, at 100 degrees, then my partial pressure here would be 760. But would my solution be boiling? And the answer is no, it wouldn't be boiling, because 55 divided by 55.5 times 760 is equal to 753. So here, at 100 degrees Celsius, my 0.50 molar sodium chloride solution will not yet boil, because the pressure is 753 torr, not 760. Okay? So you have to heat your solution more before it hits boiling. So we've seen that. We've discussed it before. Okay? What was your primary example? Radiator fluid. Okay? So when you add propylene glycol or ethylene glycol to the water in your car radiator, what are you hoping? You are hoping that the water doesn't boil over. And the reason the water doesn't boil over and your radiator is fine is because you lowered your vapor pressure by making it into a solution. And when you do that, it has to reach a higher temperature in order for it to boil. If you had your car radiator fluid and all you did in your car radiator was just put in water, it would boil over really, really easily. Okay? So we're counting on that when we add radiator fluid to your car. Okay, what are the next topics for colligative properties? They are boiling point elevation, and melting point depression. And just let me tell you that the change in temperature for your boiling point is your Van Hoff factor times your mole boiling point, okay, elevation factor times molality. For your melting point, because you depress it, it's a negative value since it's always delta T is equal to T of your solution minus T of your solvent. Okay, just there's this over a little for you. Okay, you'll find that it's a positive value for boiling, it's a negative value for melting. So, negative I, K, and put F for freezing. Let's just be consistent here. Molality. Okay, these are going to be your solvent dependent. That's going to be your solute dependent. For a molecular solute, it's 1. It's ionic and breaks up into various ions. There's going to be the number of ions that form when it dissolves. This is molality. Okay, so I, Van Hoff factor. Okay, so this tells you the number of particles. Okay, all right, K, B, or Ka, or Kf, excuse me. These are going to be solvent dependent. And then M is your concentration in molality. That's in moles of solute per kilogram of solvent. Not solution, solvent. Okay? So, let's go through and talk about it a little bit before we do an example. Okay? So, let me just bear with me when I draw you a phase diagram. Okay, so here's a phase diagram. This is pressure. This is temperature. Okay? And usually what we see okay, this is my triple point. This is solid. This is gas. This is liquid. Okay, so suppose the blue is the phase diagram for water. Okay? And so basically, what we'll say is like here, let's say this is at 1 atmosphere. This is 100 degrees Celsius. And this is 0 degrees Celsius. Okay? So, if I make a solution with water as my solvent, what happens? Well, things get shifted down. So my solution looks the same. Okay? Except it got shifted down. So here's my solution. So what are the ramifications? At 1 atmosphere, my temperature, at which I go between solid and liquid now, is lower, freezing. Okay, so what I've effectively done, you can see that now, is I have lowered my, I have lowered my freezing point. Okay, here at 1 atmosphere, where am I boiling? I'm boiling for my solution at a value greater than 100 degrees Celsius. So that's essentially what's happening when you actually put in, I'm going to spill that off there. Off back there. When I always make it into a solution, you shift your phase diagram, increase your boiling point, decrease your freezing point. Okay? So let's do a boiling point elevation, since I know for our lab we did freezing point depression. So, what is the boiling point, normal boiling point? Let's say, 1 molar ethylene glycol solution. Okay, so ethylene glycol is C2, 2, 3, 4, 5, 6, 8, 6, O2. All right. It's ethylene glycol. We know that the Kb in degrees Celsius per molality is going to be equal to 0.51 for water. We know the normal boiling point for water is 100 degrees Celsius. And let's say the density for the 1 molar solution is going to be 1.25 grams per milliliter. Okay? So, if we take a look at that, then now we can say, okay, so what do we need? We know that the change in temperature is equal to the boiling point, right, of my solution minus the boiling point of water. We also know that the change in temperature was a positive I, K, B, M. And remember, it's positive because I'm elevating, so this is going to be a positive value, right? I, because this is a molecular compound, so When we look and say, oh, it's a molecular compound, so we know that my Van Hoff factor is going to be equal to 1, because this is molecular, okay? We're given the value for water, so what we need to do is we need to just calculate the molality. So what's the equation for molality? It's the moles of solute divided by the kilograms of solvent. Okay, so moles of solute we can get. So I'm going to erase this now, and we'll start calculations. Okay? So, as before, let's assume I'm working with exactly 1 liter of solution. Okay, and we said it was 1 molar ethylene glycol. Okay, so 1 liter solution, so I have 1,000 milliliters. Okay, since it's exactly 1 liter solution, and we know the density, we said it was 1.25 grams per milliliter. So I know I have 1,250 grams of solution. Okay, now we know that with 1 liter we have 1 mole of C2H6O2. We can convert that to mass. Get something like 62.07 grams. So the mass of the water is equal to 1,250 grams of solution minus my 62.07 grams of my solute. And say I get a 1,180. Let's just keep it this way for now. It's going to be 3 sig figs at the end. 2 sig figs at the end. Alright, so that's not kilograms, that's in grams. And then if we convert that to kilograms, it's 1.188 kilograms of water. Okay, so now my molality, alright, so we can just put the whole thing into my equations. Delta T is equal to I kbm to 1. Kb was 0.51 degrees Celsius per molality, and m is moles of solute, 0.0 moles of C2H6O2, my ethylene glycol, divided by kilograms of solvent. So delta T is equal to 0.51 times 1 divided by 1.180. We get something like 0.429 degrees Celsius. Okay? This should be 2 sig figs. Now, delta T is equal to the boiling point of my solution minus the boiling point of my solvent. So we know that the boiling point of my solution would be equal to 0.43, 2 sig figs now, plus the 100, okay, degrees Celsius. We know that's always going to be the case for water. So we get 100.43 degrees Celsius. Okay? So that's how you work it when you're looking at boiling point elevation. And you can also get molar masses when we look at this. Okay? So that's what we did with the melting point depression. All right, so let's move on to our last colligative property. It's called osmotic pressure. Okay, so if I have a tube that's in the form of a U, and this is a semi-permeable membrane. What it does is it doesn't allow larger molecules to go through, but it does allow for solvent, small molecules can penetrate. Okay, like solvent. All right. So why is this important? So if I initially start out, and the pressure should be equal to my outside pressure, right? And this is basically my solvent and solvent. Now, what happens if, here, I start this way, but now I've added a bunch of non-volatile solute in there. Well, if you do this, this being almost pure solvent, this having a high concentration, is kind of like if you're making Hawaiian punch and you have your concentrate and you have your water. And when you put them together in the pitcher, they're going to mix. They have a natural tendency to mix. But what happens if you had something that separates it so you couldn't do it? Then what happens is it wants to mix, but you're restricting how it can mix by this semi-permeable membrane. And it's that restriction. So what happens is that your water is going to go through that membrane. A little taller, huh? To try its best to dilute out and you can see that it has diluted out. These are further spaced apart than here. So this is not from the outside pressure, because the outside pressure is exactly the same. The difference here is that basically it will undergo osmosis, the traveling of my solvent in order to try to dilute out here. Okay, that's called osmosis. And what will happen is it's trying to get it so that the concentrations in both sides are equal. Now what stops is that at some point gravity is pushing down on it, my outside pressure is pushing down on it, and it can't continue to climb forever. So I'm balancing those two forces. Okay, now how much pressure did this apply? And so if you have a little piston, okay, and you push it down so that it looks exactly how you started, okay, so basically this is what happens. This is osmosis, I'm traveling with my solvent through the semi-permeable membrane to try to equalize out my concentrations. When I push this down to get back, I use pressure to return to initial conditions. That pressure that you had to apply, this is called osmotic pressure. Okay? That's what osmotic pressure is. The amount of pressure you need to get back to initial conditions when you have two sides across a semi-permeable membrane that has different concentrations. Okay? So how do we determine it quantitatively? So we basically kind of look at our ideal, we're talking about pressure, right? So let's take a look at our ideal gas law. Okay, so if I look at my ideal gas law, moles over liters, isn't that concentration? R, that's my ideal gas law, or gas constant. And T, remember it's my temperature in Kelvin. Okay, so I just manipulated the ideal gas law. Now, what does this have to do with osmotic pressure? Well, with osmotic pressure, since it's a colligative property, we're going to need to know the number of solute particles. Oh, that's the Van Hoff factor, right? Van Hoff factor. I. Alright? So, and instead of using P, we use capital pi. So, pi is going to be equal to I times my concentration times R times T. Okay? So let's do an example. Oh, let's just do what is the osmotic pressure that can be exerted by a 0.50 molar sodium sulfate solution at, let's say, 37 degrees Celsius. Okay? So, we know that pi is equal to IMRT. So, let's go through and get all our values and calculate it out. I, how many particles? 1, 2, 3. Because when sodium sulfate dissolves, I have 2 of these, and I have 1 sulfate. Gives me a total of 1, 2, 3. The molarity, the concentration, 0.50 moles per liter. R, no, 0.08206 liter atmospheres per mole Kelvin. And T is equal to 37 degrees plus the 273.15. That should give us 310.15 Kelvin. Okay, and then we'll do our calculation. Okay, so let's finish our calculations. So, osmotic pressure is equal to 3 times 0.5 moles per liter, okay, times 0.08206. Let me erase this, I apologize. Liter atmospheres per mole Kelvin times 310 Kelvin. So what we get for our osmotic pressure 38 atmospheres. Okay. Let's do another example and start introducing you to some new terms. Okay. So if the average osmotic pressure of blood is 7.7 atmospheres, but concentration and molarity of glucose, C6H12O6, will have the same osmotic pressure. It will be what we call isotonic. So an isotonic solution is a solution that has the same osmotic pressure as the reference solution that you're comparing it to. So we know the formula for osmotic pressure is this. And since we're talking about blood, then our temperature is going to be 37 degrees Celsius because we're looking at the human body. So the temperature is going to be equal to 310.15 Kelvin. We're looking for M. We know R is 0.08206 liter atmospheres per mole Kelvin. And since this is a molecular compound, I is going to be equal to 1. Okay? So, let's try this. Okay? We know this is 7.7 atmospheres is equal to 1 times M. We're looking for M. And we're looking for it at 37 degrees, okay? 0.08206 liter atmospheres per mole Kelvin times 310.15 Kelvin. So, before we divide everything, let's just multiply this out. .08206 times 1 times 310.15, so I get 25 point, let's say 5, all right? And then atmospheres, Kelvin cancels out, so this is liter atmospheres divided by mole times M, and this is what we're looking for. So M would be 7.7 divided by 25.5. So I get something like 0.30 molar glucose solution. Okay? So that's how we're just using our osmotic pressure equation. So let's talk about these terms. Okay? So if I have my reference solution, we just said isotonic means that your solution has the same osmotic pressure. If you're looking at something that is hypertonic, then the osmotic pressure is greater. Okay? If you're looking at hypotonic, then the osmotic pressure is less. And oftentimes what we do is we talk about red blood cells. Okay? So if I have a red blood cell, okay, and we're looking at the outside pressure of my plasma, and my plasma is isotonic with the pressure inside my red blood cell. It's going to just look like a normal red blood cell. Okay? If, however, my outside plasma is hypertonic. What this means is that this has high solute concentration. Then my red blood cell, all of my solvent, all my water will leave my red blood cell and go out to try to dilute out my plasma. Okay, so this is called crenation of my red blood cell. Okay, if it's hypotonic, which means a low solute concentration. Okay, then my red blood cell will start to bloat. Okay, and basically, this is called hemolysis. What happens is so much water goes in, it just bloats and then it breaks. So we break. Lysis is to break, to cut open. So hemolysis is basically to break open all my red blood cells. Okay.